Okay, to start off with logarithms here, let's first look at the graph of an exponential function and see how that relates to what a logarithm is. So we have this function here, f of x equals 2 to the x power, and we've been graphing a bunch of these. So if we wanted to make a table for this, hopefully you go from -2 to 2, right? You want to have the center of the table where the exponent's equal to 0. It's usually a good location there. And then with this, we want to go ahead and fill these out. So we're going to get 1/4, 1/2, 1, 2, and 4. And to go ahead and plot these, this is the same type of graph we're used to, right? We've been doing this. We know that it has a horizontal asymptote at y equals 0, right, which we might show here. We know it has a domain of all reals. And we know it has a range from 0 to infinity, right? So we have all this. So then if to plot these points, that would be our exponential function, right? This is our graph. F of x equals 2 to the x, or you could think of it as y equals 2 to the x. Maybe would make it a little bit maybe easier to think about. But that's something that we've been doing a bunch. Now what we're going to find though is that logarithmic functions are the inverses of exponential functions. So, and we'll define this a little bit more here shortly, but the most basic way, if you think back to when we did inverses a few units ago, is the x's and y's just switch places, correct? So in terms of the function, if you wanted to find the inverse function, well, you would just say x equals 2 to the y power, right? I just switched the x and the y's. In terms of the table, you would just switch the two columns. That's going to give us, what, 1/4, 1/2, 1, 2, 4. Right, so that's the most basic way to get an inverse, is to plot points for the original function, flip them all, you get the new function. Now, we're going to use the logarithm notation in the function, because this is not a great function to work with, because we're used to seeing it say y equals. But here, in order to get the y out of the exponent, we're going to have to use logarithms. That's the main reason that we use logarithms now, is to have an inverse function for an exponential. So if we graph this, it's going to be at 1/4 -2, 1/2 -1, 0, 1, 2, 1, 4, 2. If you notice here, if you think I keep putting more and more negative numbers in for y, this base is still always going to be positive, correct? So we're going to have a horizontal or a vertical asymptote at x equals 0. And it's going to look like that. So again, for this function, we have a vertical asymptote. I think I may have misspoke. A vertical asymptote at x equals 0. And then we know about inverses, or we can see it from a picture, but also we know the domain and range are going to flip-flop. Right? So for this one, the domain would go from 0 to infinity, and the range would go from -infinity to infinity. Okay? Something you might notice here is when you have these logarithmic functions, and once we get them right and using our format, when you evaluate a log, you're never going to get you're not going to get a negative number inside the logarithm. It just won't work out for you. So we'll look at that. So here's just a sort of a graphical idea, right there, a reflection across the line y equals x. Right, you have a log. This would, and we'll see why in a second, this will be written normally as y equals the log base 2 of x. And we'll look at how to convert from one form to the other. That's what that blue graph actually was there. Okay, so the most important part that we're going to have with logarithms, where everything else comes from, is this definition right here. Okay, we looked at our graphs earlier on the board. You know, we saw that for the inverse function, you had the y kind of stuck up in the exponent, which is going to be a problem. You won't be able to type it into a graphing calculator. You're not going to even be sure it's a function sometimes because of the different things. So what we can do here, and this is the most important definition again, is if you see a log base b of x, so we read that as log base b, or it could be a 10, log base 10, or it could be a 5, log base 5, and so on, equals some number y, we have to be able to rearrange it from logarithmic form over to exponential form. Super, super important here. So the way I like to do this, and there are some different ways, and they're all just as valid as long as they're correct, is I know that this b right here is called the base, correct? So it's the base of the logarithm. It's a subscript. It's a little bitty letter. But I know that when I write exponential function, the first thing I need is a base, right? So whatever was down there as the base is going to become the base of the exponential. Now the other way so that's my one piece I know. And then I notice here that x and b are on the same side. They're together. Here they're opposite, right? Here the y was all by itself. Now it's with the b. So I always think that, one friend's left out in one form. Everybody wants to be by the base, right? But anyways, that's kind of how I think of it. But you just got to find a way to make sure that that works. Because we'll look at some today, and when they have numbers in them, usually they're pretty, you could probably spot them pretty easily. Sometimes when you get multiple variables and stuff, or maybe common logs or natural logs, which we'll look at here soon, it could get a little bit more complicated, would be the thing to think about. So, on the bottom of your worksheet here, we have a couple: rewrite in exponential form, rewrite in logarithmic form. So just to run through that process, and then I'll get a chance to try some of these. Is here we have the log base 3 of 81 equals 4. So 3 is the base, correct? So if I want to switch forms, it's going to be 3. Now do I take it to the 4th or to the 81st? Take it to the 4th. Because the log will equal the exponent. This is the exponent, correct? 4 is the exponent. So 3 raised to the 4th power equals 81. That's how that would work. The next one's one of my favorites, right? Log base 7 of 7 equals 1. Notice here we have the base matches the argument, right? The thing inside the logarithm. And what we're going to find is every time that happens, you're going to get 1 if they match. So we weren't asked to solve it. It's already solved or simplified. But we are asked to, we're going to say 7 to the 1st power equals 7. Maybe look at a couple the other direction, and there's a couple more on your worksheet there. But here we have 10 cubed equals 1,000. These are nice too. They're all true, right? Kind of get used to seeing how they look when they're true. So with this one, we have a log. We're going to write it in log form. Now I'm going to go ahead and write log base 10. Soon we'll learn that you don't have to put the 10 there. It's what's called a common log. If it's ever missing, the 10's what's there. Right? It's kind of the fill-in piece. So we could say log base 10 of 1,000, because that was by itself, equals, we know the log equals the exponent, correct? So how we can move those around. So again, the base became the base of the logarithm. The 3 that was the exponent is now by itself. The 1,000, which was the answer, is now inside the logarithm. So people look, you say 210 cubed equals 1,000. That's what that's telling us here. So now this next one, it'll be a log base, what would our base be? 81. And then of 9 equals 1/2. Okay. Hopefully that seems boring and really easy, because that's a great sign, because we just need to do it pretty automatically. It's one of the ways we can solve. A lot of times we have to make sense of these problems and what they're asking. That's a great way to try it, to get that straightened out. Okay, so let's try the rest of those on the front. So again, we just want to run through 4 basic properties that will help you to simplify logarithms. If you're asked to evaluate, what's the log base 2 of 8? This is a way that you could get led through that. So the first one here is, and we saw some examples here on the earlier worksheet problems. If I have the log base b of b, so if the argument and the base of the logarithm match. So what this is saying, it's saying b raised to what power equals b? 1. And that would just be the 1st power. Does that work? So if they match, they pretty much cancel. Kind of think of it that way. kind of some results of that is if you have the log base b of 1, this is a nice one. So you have b raised to what power equals 1? 0. Yeah. How about the log base b of b raised to the n power? So if you think about our form, it's saying b raised to what power equals b to the n power? Just n, right? So does it look like the log and the base are canceling? I'm not sure that's the right mathematical term, but they kind of undo each other. They're inverse functions. They undo each other. And the last one, just as true. It comes up just as often, but it's really pretty strange looking. And that would be if you have a b raised to the log base b of n. So here, this is actually not in logarithmic form. This is in exponential form right now, the way it's written, right? Because it's an exponent. So it's saying b, so this would, well, so b raised to the log base b of n is going to equal some value here, correct? Any guesses what it would be? Yes? It's n. Yeah, it's n. They basically, they're inverse functions again, correct? They undo each other. So it would just be n. If you think about, if you wrote this is in exponential function, correct? If you put it in log function, it would be the log base b of n equals the exponent, which is the log base b of n. So if they equal each other, then n must equal n. And these, again, we'll come back to these properties a lot. They're really just handy to know, really helpful to work with. So for a lot of these, you can simplify them purely just using these properties. So if we look on the back of our worksheet, we're asked to evaluate the log base 9 of 81. And I'll show you a couple different ways to evaluate. But hopefully, we realize that since logs are exponents, correct? We should be thinking in terms of powers, like how many is this squared or cubed or things like that. Well, as we look at this one, I have a log base 9. I know that 81 is just 9 squared, isn't it? So since that's the case, let's go ahead and rewrite this as the log base 9 of 9 squared. And that's just an instance of this third property, isn't it? So since they match, this would equal 2. So you could write as your answer log base 9 of 81 equals 2. That's one way that we can evaluate them. Pretty straightforward one there. Let's look at some other ones that may or may not be as simple. I like this. We have this log base 4 of 1/8. Okay, which, now with this one, for this log base 4 of 1/8, we want to realize that when you're doing this, we know that 4 and 8 are both powers of 2, don't we? That's really important because we know that. It'll be helpful. So what you might do here, we're probably not going to get it to look as nice as that first one. It's just not as nice of a problem. But what we can do here is if I'm stuck and I can't see a path like this one, hopefully we could kind of see that path, right? Work this way through here. I'm not getting a great feeling. So I'm just going to say that the log base 4 of 1/8 equals x. I'm just going to say, well, it equals some unknown, right? I'm just trying to find the unknown. But then once we do that, let's go ahead and switch forms because I'm pretty much stuck on this form. So we'll say 4 to the x power equals 1/8. Okay. Now at this point, if we can get both sides to have a base of 2, we'll be able to solve this. So I know 4 is 2 squared. Pretty confident on that one. So we have 2 squared raised to the x power. Well, 8 is 2 cubed, so that's 1 over 2 cubed. Now here is a base to a power to another power, so we can multiply the exponents. So we have 2 to the 2x. Now here, if I want to move this base up into the numerator, what happens to the exponent? It's negative. So you get 2 to the 2x power equals 2 to the negative third power. Well, the exponents are equal if the bases are equal. So we get 2x equals negative 3, x equals negative 3/2. Would be our answer there. To check that, you would just say 4 to the negative 3/2, right? Which, remember, the squared on bottom is a square root, correct? So that gives you 2 to the negative 3rd, which is 1/2 cubed, which is 1/8, so it does work out there. So those examples there. There's one more type that shows up here that's kind of silly. Now, everything we've done so far, and really with the exception of these two evaluates, this being one of them, you wouldn't use a calculator on these. I know that you can just type them in your calculator and you get an answer, but we're going to work on evaluating them by hand, right, finding their values this week. So you'll be given ones that you can evaluate by hand. But like this one, and then over here it had, these are kind of silly. We'll run through them together. Like you could do these by hand, but why? Like they're just way too crazy looking, kind of bizarre. What do you know about the number 121? Anything?
It's 11.
It's 11 squared. You know anything about 1,331? It's 11 cubed actually, but yeah, it's big. It's just kind of weird pattern. So once you know that, we might be able to do it just like the last one and say the log base 121 of 1331 equals x, right? So we're just going to try to kind of force exponent values here. So when I switch forms here, it's going to become 121 to the x equals 1331. And again, this process of just kind of working or manipulating these and getting them to solve is really beneficial in lots of ways. So 11 squared to the x is equal to 11 cubed. So 11 to the 2x equals 11 cubed. So x equals 3/2. So I guess 3/2 is the answer there. It would make sense here because you're doing 121 to the 3/2. So the 2 on bottom means you square root it to get 11, right? Then 11 cubed to give you that one. So there's another one like that if you want to goof with it. We could go over it later if you want, but it's on there. What I really would like you to do is just make sure you get these practice problems done. Just take the rest of class, work on them. If you want to work with your neighbors, that's fine. But just try and make sure we're getting a handle on the kind of basic level logarithm stuff so that we can be successful. There's also a Delta Math out there on, I think it's due Friday. It's called Logarithms, number 1. It wasn't a great name, but I went with it anyways. So.